Okay, hi everyone. Can you guys hear me? So welcome back to HITB Virtual Labs by CSQ. So I hope you guys had a great time yesterday for day one and also the CTF. Right. So yesterday we discussed on the overall vehicle architecture, a little bit about the CAN bus protocol, CAN frame, car hacking tools, and some practical hands-on activities on ICSIM. So today will be a more lecture format that we'll be discussing through the different protocols within the vehicles in brief details. So the ISO-TP protocol, the UDS, FlexRay, MOS, LIN, and Automotive Ethernet. Right. So again, my name is Alina. Thank you for joining us. With me, I have Edmund. Pace is on the line as well, and Chun Yong. Me now. Right. So we are from the Car Security Quarter, CSQ, and we are part of a wider cybersecurity community here in Singapore called Division 0. And we power the ASRG Singapore chapter. Right. So the goals of CSQ is to facilitate and promote automotive cybersecurity awareness to the cybersecurity community here in Singapore. And so mainly what we do is in Singapore, cars are very expensive. So we wanted to empower like-minded security enthusiasts in getting hands-on experience. So in order to do so, we actually built vehicle test benches to create a safe environment for people. And we also do some ground-up research and perform community engagement so that we can eventually contribute to the automotive security industry. Right. So Emma will be going through the ISO-TP protocol, UDS, and FlexRay.
Yep. Hello, everyone. Can you hear me? Okay. So I'll be giving a brief introduction of the different protocols in the vehicle. So starting with the ISO-TP protocol. So ISO-TP protocol is an international standard used to send data packets over the CAN bus. So yesterday we learned about the CAN frames, which 8 bytes of data load. So ISO-TP actually extends this limited data load to 4095 bytes up to. So the most common use for ISO-TP is actually for diagnostics over the OBD2 or the diagnostics over CAN. So what is the ISO-TP and how does it look like? So ISO-TP has 4 frame types: single frame, first frame, consecutive frame, and flow control frame. So what denotes as a single frame is actually any data packets that is only up to 7 bytes of data. And the communication between the first frame and consecutive frames is for anything above 7 bytes. Next slide. So packets that are larger than 7 bytes are actually segmented into first frame and consecutive frames. So transfer always starts from the sender sending the first frame, which the receiver will receive, and it confirms this first frame by sending back a flow control frame. Once the sender receives this flow control frame, it will continue to send out the rest of the frames that's inside the data packet. So how many frames and how much time between the frames is actually controlled by the block size and the separation time. And this is all set by the developers for this ISO-TP protocol. So in socket CAN ISO-TP, much like the CAN socket CAN tools, there's ISO-TP send, much like CAN send, ISO-TP receive, sniffer, wiretap, and so on. So in the next slide, we have an example of how the ISO-TP is used. So from here you can see where we echo the requested session code and then pipe into ISO-TP send, the interface, which is the SL-CAN0, and then the sender, denoted by the -S, and the receiver. So which brings us to the next topic, which is the UDS. So as mentioned, ISO-TP is diagnostics over CAN, and UDS is a diagnostic service which is handling diagnostics over OBD2. So this is on session layer and the application layer of the OSI model. The UDS is only capable to actually be a read-only. So it provides the following functionalities, which is the fault diagnostics, DTCs, upload-download capabilities, meaning you can actually program the software or download the software. A remote routine activation to start routine remotely using server memory, and also rewriting ECUV by data transmission read-write capabilities. So the UDS actually to do anything to the ECU, they have to unlock diagnostic session. So in normal use cases, UDS is actually to read vehicle information without affecting the vehicle operations. And this UDS uses ISO-TP protocol to send a larger data output over CAN bus, allowing chaining of multiple CAN packets. So UDS actually has a request and response format. Like the ISO-TP, they have the sender and receiver. So UDS also uses that. And the specific method to receive response data is actually through the arbitration ID and whether you get a positive response or a negative response. So the arbitration ID is actually, there's two types, much like the CAN frame. So the CAN frame, there's the normal CAN 11 bits ID. There's also the extended CAN frame, which is 29 bits ID. So in this example, the picture, we are actually using the 29-bit ID. So you see the 18DA11F1, yeah, that's for 29-bit ID arbitration. And then from the 1101, you can see we are sending out to the receiver, but we receive a negative response back, which is 7F. So all negative response are returning 7F data, and all positive response will return back 1101 plus 04. So you receive 5101. Next slide. So the interface here is the SL CAN. The bracketed is the number of bytes in the CAN message. The next number, which is 03, is the number of important bytes that you're sending out. So 7F1013 is the number of important bytes, which actually means anything in this UDS. The rest of the bytes are actually just filler numbers. So now we'll go on to the FlexRay protocol. So this protocol is actually developed by FlexRay Consortium, which was started by BMW and Daimler when they wanted a new network other than the CAN. So the CAN is quite a slow protocol, which is up to 1 Mbits per second. This FlexRay is actually 10 Mbits per second, and it's more faster and more reliable in the sense that it allows for clock synchronization. However, it's very expensive, so it's not usually seen in common cars, but on higher-end vehicles. So BMW X5 has this protocol. So the common application for FlexRay protocol is to be used in critical safety components such as the powertrain, drive-by-wire, ACC, adaptive cruise control, and the suspension. So this is how the FlexRay protocol looks like. It contains header, payload, and the trailer. So the header is 40 bits long, consisting of the status bits, which is 5 bits, frame ID, 11 bits, payload length, header CRC, and cycle count. So in FlexRay protocol, the payload is 254 bytes long, which is much bigger than a CAN frame. And the trailer is containing 8 bits of CRC used for error detection. Yep. So the disadvantage of actually the FlexRay is it's operating at a lower voltage level, and the asymmetry of edges leads to problem in extending the network length. That's why it didn't get as popular as the CAN was. Yep. With that, I'll pass back the mic to Alina to introduce the LIN protocol.
Okay. Thanks, Simon. So, right, the LIN protocol itself, the short form name is called LIN. So the full term is called Local Interconnect Network. So the LIN protocol is a low-cost serial protocol designed to interconnect other components and complement the CAN network within vehicles. The common automotive application usage are actually the slower applications within the vehicle, for example, like door, seats, AC, sunroof, rain sensors, anything that's not critical to the vehicle. So usually anything in the vehicle that has to be in critical components has to be of higher speed. So the LIN protocol itself, it's pretty slow, but it's actually cheaper to implement. Right. So the network topology is using a master and slave network topology. And similar to CAN bus, it actually broadcasts, it has a broadcast network itself. And the slave can support up to 16 nodes. And some of the hardware being used to decode the waveform of LIN bus can be, for example, your oscilloscope, logic analyzers, for example, Celare, and bus analyzers. Cheaper bus analyzers are like your bus pirates, which is not shown over here. Right, so the structure and communication of the LIN protocol, since they actually use the master and slave architecture, it operates with the master node looping through the slave nodes, polling for information. So the master header will actually transmit to the slave, and they will actually respond with 8 data bytes. And then the LIN protocol itself is actually a header and response structure. So the header, you can actually see that there is a break field over here, which is called the SYN break field. So the SYN break field itself, it usually contains 14 to 20 bits, and it actually indicates the start of frame to all LIN nodes. And then you have your sync bit to actually determine your baud rate used by the master node, and your identifier, which is your ID, which identifies the LIN message sent. So the ID is similar to what you guys, if you guys attended the CAN bus lesson yesterday, it's actually the same thing. So in this case, it's just 6 bits over here compared to CAN bus, you have 11 bits. And you have your priority 2 bits. It determines the validity of the ID field. And of course, for your response, it usually contains your data field. So usually 16 to 64 bits. And then it transmits with this sequence 2, 4, or 8 bytes of data when the LIN slave is being pulled by the master. And then you, of course, have your checksum, which is similar to what you have in the CAN bus. So most newer vehicles have more than 10 plus LIN nodes within the whole network architecture of the vehicle. Right, so here's a comparison of the LIN bus, CAN bus, and FlexRay bus. So LIN bus, unfortunately, operates at a higher voltage level, so 12 volts, and CAN bus 5 volts, and FlexRay is up to 3.5 volts. LIN bus is lighter compared to CAN bus and FlexRay bus because it only uses single wire. Compared to CAN bus and FlexRay bus, it actually uses twisted pair. And then the medium itself, LIN only has a single master that serves as a gateway to CAN bus. Compared to CAN bus and FlexRay bus, it's multi-master, except that CAN bus is using CDMA, FlexRay is using TDMA. Right. So as I mentioned earlier, LIN bus is used for non-critical systems. So it operates at 20 kilobits per second. As compared to CAN bus, it's 1 megabits per second, and FlexRay, you have 10 times more of the speed. Right. For IDs, 6 bit, and compared to CAN bus, 11 bits, or as Edmund mentioned earlier, 29 bits. So usually you have your CAN-FD that can be applicable for any of this instance. CAN-FD is actually up to 128, but they have all different applications. CAN-FD is pretty similar to CAN bus as well, right? So LIN bus is cheaper to implement compared to CAN bus. It's moderate, and FlexRay is very expensive. That's why on lower end vehicles you don't really see them, right? Okay, so moving on, we move on to the MOST protocol. So in short, MOST means Media-Oriented Systems Transport Protocol. It can be usually found in the infotainment system, used to transmit audio, video, and media via the plastic fiber optic cable. So the most topology actually features a ring chain design. Usually you see daisy as well, but the most common ones are ring. And it allows high-speed networking subsystems to be connected together in a multimedia network used for multimedia and infotainment applications. And then it can actually support low cost and low overhead connectivity. And the good thing is it can actually support up to 64 maximum devices in the network. And most technology is commonly seen in, again, BMW or the, I think newer end vehicles, they, for Japanese make and Korean made vehicles, they do have that as well. Presently, we're actually on our test bench, the second test bench, we do see it for our second test bench, the MOST protocol. And MOST protocol is governed by the MOST Corporation. So the speed itself is high speed, about 25 megabits per second or 50 megabits per second. And they actually use unshielded twisted pair also, not only like plastic fiber optic cable. Right. So for the MOST protocol, they have a few masters that exist in the MOST network. So for example, the timing master, network master, connection master, and power master. So the timing master controls the timing of the network and synchronizes the device. And the network master sets up the network and allocates addresses to the devices. And then the connection master ensures the synchronous communication channels between the devices. And then power master, of course, handles your power up and shutting down of the device. Right. So within the network itself, the MOST protocol has 3 communication channels. You have the control channel, asynchronous channel, and synchronous channel. So the synchronous channel itself is used for stream data. It supports continuous data streams that requires high bandwidth. And for your asynchronous channel, it's used for packet distributed data, which allows packet-oriented transmission with large block size and high bandwidth. And lastly, your control channel is to control low speed data. So lower bandwidth, like for example, 10 kilobits per second, and shorter package length. And there are actually different types of data frames for MOST. So earlier on, I mentioned the 25 megabits per second and 50 megabits per second. They are actually for MOST 25 and MOST 50, right? So MOST 25 itself, they support the optical transport medium, and then they usually present with about 60 bytes of data frame. And then for MOST 50, it supports both optical and electrical transport medium, and supports 117 bytes of data frame. Right, so over here, as you can see from the diagram, the OSI layer. So MOST itself actually uses layers 1 to 7. So for those of you who are probably new to networking and stuff, the OSI layer defines your networking structure. So for layer 1, for physical, it actually supports your physical medium, which is your physical optical interface, or your electrical optical interface for MOST 50. And for data link itself, it acts as a MOST transceiver. So where you have your NIC in there, your network interface controller. And for layers 3 to 7, or network transport session presentation and application layers, it actually serves as a communication block for the application. Right, so you can see here over, you have the function block and stream service and stuff. Right. So earlier I mentioned that the MOST device itself can be broken down into 3 different parts, which is your physical network and your function blocks. So network service contains your NIC, network interface controller, and your MOST transceiver. And the function blocks on your layer 7 application acts as a master and slave function. So the function blocks itself, F-blocks actually uses functions and slaves called the controller, and the controller sends the commands to the slave and receives the data from the slave. So controller itself acts as a master over here. And controllers are usually connected to the HMI, which interfaces the users to issue commands to the slave. So for example, if you have an infotainment system and you are trying to go to the media or try to make a phone call from the screen, that is called the HMI, your human machine interface. So that itself is connected by most and other different protocols as well. Right. So over here you can see some pictures that we took apart our infotainment system for test bench 2. Like for those of you who played the CTF, you would have seen the screens and the cluster meter. Beneath the screen, there is an infotainment system that we hid it within the foam. So it has a Morse cable over here, as you can see on the orange color cable, and it emits a red light with usually the wavelength of 650 Newton meters, and it uses LED for the transmitter, and the visible uses a pin photodiode. So the physical medium, as you can see, is a plastic optic fiber. As you can see within the internals, we tear apart. It actually has about 5 to 6 layers. But as you can see, within itself, it actually connects via POF as well. But we haven't took apart the POF to see what's that. But here are the general pictures. Yeah. Okay. So moving on, we have the automotive Ethernet. So the automotive Ethernet is similar to the computer Ethernet, and it's used to design and replace or to complement CAN bus in our usual real-world case scenario. And due to the rising demands for bandwidth and the quality of service, a lot of vehicles actually require, like, for example, autonomous vehicles and V2X technology. They actually need a lot of bandwidth and QoS. So in order to support that, we actually have to integrate automotive Ethernet in there. And automotive Ethernet comes in two forms. It's 100 base T1 and 1000 base TX. I have a comparison table with the standard automotive Ethernet that I will show you guys later. It allows clock synchronization again, and then it supports the bandwidth up to 1000 megabytes per second, which is your 1000 base TX medium. However, a switch is required in this case, and it offers bidirectional traffic flow compared to your regular Ethernet, which you need 2 different network cables for that. And common applications include the most popular ones are your ADAS system, your body and comfort systems, your infotainment systems, and powertrain systems. Over here, you can see that the automotive Ethernet on the diagram over here is actually a linkage between like CAN and FD, ADAS, and different other systems. Right. So we have for the automotive Ethernet itself, they have like diagnostics as well. So automotive Ethernet, instead of using do-CAN, which is your diagnostics over CAN, it uses diagnostics over IP, which is do-IP, which uses your ISO 13400 for the automotive Ethernet itself. So under the OSI layer that I have a short summary table over here, you can see that layer 1, in comparison to CAN bus, layer 1 itself and layer 2 actually get CAN bus. And for DOIP, it's your 100 base TX or your 1000 base TX in Ethernet. And then layer 3 and 4, it's basically ISO 1567-672-2, your do-CAN itself is your ISO TP protocol. It's in comparison to DOIP, whereby your layer 3 you support IP and layer 4 you support TCP. And then layer 5 itself, basically your UDS standards, ISO 14229, and then your layer 6 and layer 7s are actually the same. So this is the overall architecture of like the difference between DOIP and do-CAN. Okay, so earlier on, I mentioned the physical properties of the automotive Ethernet. So similar to what we have for the Ethernet, it actually uses a twisted pair wire to transmit and receive data at the same time. So it's bidirectional compared to the standard Ethernet, whereby it's only single direction. And it's actually used to design for weight reduction purposes. So for example, in your car itself, 2/3 of the weight are actually attributed to the wiring harnesses in the vehicle. So all your CAN bus, all the wiring harnesses are actually really, really heavy and really expensive. So for automotive Ethernet itself, it's much lighter. So the connector varies via different OEM as well. So for your standard Ethernet, you use your RJ45, and for automotive Ethernet, it depends on the manufacturer and the OEM. And automotive Ethernet is much shorter compared to the standard Ethernet. So standard Ethernet is 100 meters, automotive Ethernet is 50 meters. Data rate is as follows, it's the same, 100 megabytes per second, 100 base, 1000 base TX is 1000 megabytes per second. Right. Okay, so we come to the end of the content for today. It's a bit early, so if any one of you have any questions, feel free to ask us, or we can talk a little bit more about the CTF. Okay, so basically, I believe most of you have participated in the CTF yesterday, and some of you are unable to work on the bench one, right? So bench 2 was solved by Goose CTF. So just a slight hint, if there's a hint for you to purchase, go ahead and purchase it. It will be easier for you to solve. And I would urge you guys to work on the virtual benches if you haven't, to solve and get a better understanding of how Canvas works before you move on to the physical bench 1 and bench 2. We will be releasing more questions today. Some of them are really challenging, and we'll also be releasing a UDS question, which is focused on getting the security algorithm for it. So that would be a very high point question, and see if anybody can solve that. Right. So a little bit more about the CTF today is you can create an account on ctf.carsecurityquarter.org. There will be joining instructions for you sent directly to your email address that you have registered. So do create a Twitch account for you to join the queue on Twitch, and then join the HRDB Discord channel. Go to the Car Security CTF. And then once you have registered an account, you have to join the specific VPN network itself. So you have to give the CSQ Discord admins the following details, and then you can actually join that. Okay. So yeah, please queue for only one bench at a time. Yeah, and then the format to join is create an account on Twitch. First, join the queue on Twitch, inform the team in Discord, and then that you would like to play. Only one account is needed, and then go to ctf.carsecurityquarter.org/video, and then you see all the streams there. So once it's your turn, your CSQ crew will inform you on Discord. Once you have 3 minutes left, they will inform you as well. So happy playing. And if you guys have any questions, feel free to ask us, because we are a bit early over here. Right. So if there are no questions, we will leave this stream on. Or if you guys want us to go through day 1 materials, we can as well. So if there is no questions, I'll just leave the stream on, and we'll go and set up the CTF. But we'll be monitoring the Google slides itself. So you can post your questions over here. If not, we'll just end the stream for today. And we'll see you in the CTF. Sorry, I just saw a question. So since LIN bus is 12 volts, does the car use the LIN bus to power the power door lock, for example, or does it draw power from another source? So all cars draw power from the battery source itself. Your car battery is capable to power up to 12 volts, or if let's say you purchase a more expensive battery, can support up to higher volts, and it draws automatically on its own. So the protocols know what to draw. So for example, for our test bench 2 setup, so even if we put the bench to 13 volts, it will only draw the current and voltage that it needs. It will not overdraw. So the devices also have an overheating and over current supply protection and over voltage supply protection. So it knows how to draw all the devices, and it comes directly just from the car battery itself. Sorry, there is a question over there. It says here on Google Slides that within a car, would there be a single network using one protocol to control the car, or can there be multiple networks within the car that govern by their own protocols? So I'm not really getting the question. Do you mean that would there be just one protocol that governs all the other protocols? Do you mean that? So basically, there are actually different protocols within a vehicle. So you have your CAN bus, your LIN bus, your FlexRay and stuff. So they can all work with each other via a central gateway. So the central gateway itself actually does all the translation. Like, for example, we have our central gateway in our test bench 2 as well, in the CTF, which is also hidden from sight. The central gateway actually translates the most protocol to CAN bus and all other devices that portray on the cluster meter. So if we remove, for example, if we remove the most cable from the cluster meter or the infotainment system, some of the messages will not pop up. So there is no one single protocol that governs the whole single network. So multiple protocols are talking within the network itself in the car. So I hope I answer your question for that. So there are other ways to interact with the car as well. There are also other remote ways. So for example, so for higher end vehicles, right, there is, for example, your key fob contains your VIN, your CAN traffic. So for example, one of the German OEMs have the ability to include all of the vehicle vehicle information in the key fob itself. So if you present your key fob to the manufacturer in the workshop, they can actually plug in your key fob and withdraw all the information from there. But it only appears on higher end vehicles. But to interact with the vehicle itself, like for for a start, it would be better to connect via the OBD2 port, and you will of course need like a CAN translation device. So for example, like CAN to USB or like Cannibal Pro or PyCAN. All these devices actually allows you to communicate from the vehicle to a laptop and vice versa. So there are also different ways to do so. It depends on whether you tap into the CAN traffic of doing so. How would you tap into the CAN traffic? So one example that we learned from our test bench, current test bench itself, is that the funny thing is we couldn't draw any CAN messages from the OBD2 port. So the manufacturer actually blocked some of the CAN messages, like most of the CAN messages from the OBD2 port, and we couldn't interact with the car from that. So what we did was we actually we did a man in the middle and tapped into the middle of the traffic of the vehicle. So from there, we were able to actually get the messages out. So the interception lies from the cluster meter to the central gateway itself. We actually tapped from the middle and we were able to extract CAN messages. So that is how, like the players now who are playing the test bench 2, that's how you interact with the vehicle. It's not via the OBD2 port for the test bench 2. However, for the test bench 1 that you guys are playing on the CTF, it's directly, we can interact directly via the OBD2 port. So there are multiple ways to interact with the vehicle. It depends on how creative you want to be. Some of them, like even the folding mirrors, you have wires over there. There potentially might be CAN messages as well. We've seen cases of people trying to interact with the vehicle by taking out the side mirror and tapping into the traffic from there. So if your CAN bus messages or CAN messages from the side mirrors itself, we can do so. So it depends on how you want to actually break your vehicle in that sense. I hope I answered your question. Okay, so Let me read out the question. Currently, are there any security measures or standards to prevent cars from being hacked? Is it possible to hack a car remotely, or would somebody needs to be there physically? Okay, this question is, let me answer the second question first. So it is possible when you have gained physical access into the vehicle and you manage to hack it remotely, like placing a backdoor in the, for example, I will quote the Charlie Miller and Chris Villasek Jeep Cherokee case. So once they have gotten access to the infotainment system, they were able to return back into the infotainment system and basically compromise all the way to the UDS level, the diagnostics level. So somebody doesn't have to be there physically after they have reverse engineer. So it's similar to how you have in your computer's case, like somebody placing a backdoor in your vehicle. So are there any security measures or standards? Yes. So currently there is a ISO standard being worked on right now. I forgot the ISO name. I think it's just give me a moment.
21434.
Yeah, 21434. Yes. We've been doing this day in, day out. I forgot the ISO name. Yeah. So ISO 21434 is currently being worked on. And and globally we have the WP29 standards. They are also focusing on connected vehicles and autonomous vehicles, the cybersecurity standards of that. In Singapore, we have the Technical Reference 68, TR68, released by different consortiums and LTA. So that itself can actually state like the security measures from the cars being hacked. And also in ECUs, you have something called the HSMs, your hardware security modules, which like sort of like encryption to prevent the ECU from getting hacked as well. And even in the UDS, the security access session itself is not that easy to break into. So fundamentally, yes, there are security measures being there, even though that it's not as advanced as compared to computers. So there is another question. How do you find out the functions of CAN IDs and other than playing with the car buttons? Is it possible to brute force and use other techniques? Yes. So it is possible to brute force, and there is also other methods such as fuzzing. So I would highly suggest you guys, if you guys want to play the CTF, go check out the CAN YouTubes that what Pace and Chun Yong mentioned yesterday. In CAN YouTubes, there is already a built-in function for you to do fuzzing. So check out how to utilize that. There are also other fuzzing methods out there. There are other different tools, commercial tools. You have your Vector, your VTest Studio, your Intrepid Control Systems, your Vehicle Spy. For open source tools, you have CAN utils, Socket CAN, which is basically the same thing. But yeah, as long as you can actually do fuzzing on CAN bus. Yeah. I hope I answered your question. Are there brakes? Okay, another question. Are there brakes, accelerators, and steering wheels when connected same bus? What protocols are used to control it? Okay, so brakes, usually you have your flex ray. Steering wheel, you have your lane bus. Your accelerator, because if it's drive-by-wire, is usually like flex ray. And usually you wouldn't really see much CAN bus inside there, but there are also cases, it depends on OEM, CAN bus presently in there as well. So steering wheel, usually your LIN bus and all, but some of the manufacturers prefer to use automotive Ethernet. So it depends from manufacturer to manufacturer. So the ones that we went through earlier, these are the commonly used protocols in vehicles. There's a new question. How does the car know that the key fob is nearby? So basically the key fob itself, it has the same VIN, the vehicle identifier number, as the vehicle. So I've been asked this question by my friend before, like if you have two similar vehicles and one key fob, which how does the key fob know which door to open? So for example, so basically the key fob must have the same VIN as your vehicle so that it knows how to open that vehicle. So it does by detection of VIN, and your key fob itself is actually battery powered. So the way it actually detects is that there is CAN bus traffic going through as well. So in that case, it's when you are near the vehicle, and sometimes it has NFC or Bluetooth technology in them. So it detects during that way. Yeah. So, but the most important thing is you must have the same VIN that's coded into the key fob in the vehicle. So for example, one of the things that CSQ has been doing right now is that we have multiple key fobs and we have a lot of blank key fobs as well. So one of the things that we are doing is we are going to clone the key fobs into the blank key fobs, and we are going to do like roll jam attacks, replay attacks and stuff. Just that we haven't really had the time to do so because we've been busy building testbench 2. But now that testbench 2 is up, we will probably do more of that. And in future, the presentations might be more on key fobs, replay, relay attacks as well. Yes and no. Okay, so for testbench 1, yes, we have scrap car parts on that. Testbench 2 is not. So testbench 2 itself, we purchase it from, there are different sources from eBay. We didn't really get the testbench 2 parts from scrapyards in this case because for testbench 2 it's a pretty new vehicle. It's actually a 2016 vehicle. So we don't really buy scrap parts for that. And of course, brand new is too expensive. So I would say second-hand parts rather than scrap car parts. Because in Singapore, as you know, that we have like something called the Certificate of Entitlement, COE. So COE lasts for 10 years. So vehicles that are usually found in scrapyards are like maybe 2006, 2007, probably now up to 2010. Unless the vehicle has a major accident or is declared total loss, then you'll find those parts. If not, it's actually really hard to find scrap parts in Singapore. And especially for testbench 2 is a fairly new vehicle. So we actually have to source for second-hand parts to purchase. Okay, so we have a new question. How does different modules in the car authenticate each other? So to answer this, so CAN bus and LIN bus, like I've mentioned earlier, is a broadcast network. So think of it like UDP. So they don't authenticate each other. So it's a blast, and you actually receive all the messages on the other end. The ECU itself, how they identify each other itself is through the ID, the specific identifier number, the CAN ID. So for example, if you guys played the CTF yesterday, you have different IDs over there that is running through, right? So there's no authentication involved. How the ECU knows that the traffic is for them is through the data bytes and the ID. So there's no authentication in there, except for UDS. UDS, the typical application for UDS is when you go to a vehicle workshop, when there's something, some issues with your vehicle. So what the mechanic does is they actually plug the cable via the OBD2 port to your vehicle to diagnose what's the issues for the vehicle. So in that case, if let's say the technician needs further permissions, not say permissions, but further access to your vehicle, they will actually have to unlock the security access session to actually access the vehicle itself. So in that case, the seat and key, there is authentication over there, but that is only that for UDS. But in general, there's no authentication within the vehicle itself. So it's UDP all the way. So we have another question. Is the UDS only available for OEM repair shop, or the authentication is able to be cracked? Yes. So in general, OEMs and all the automotive like repair shops have the UDS, and diagnostic machines have the UDS code. So it depends on how creative you want to get the authentication or the cryptographic keys to be cracked. Because in general, OEMs will not tell you what they use. They won't say that is AES, DES or something. They will not even tell you the encryption strength as well. So it's up to you on how you want to reverse the software and if you can get the software. Okay, no questions, guys. Thank you for joining us and thank you for staying with us. I will see you guys on the CTF session.